These are the notes for AP Calculus on the topics of higher order derivatives and position, velocity, and acceleration. So higher order derivatives refer to derivatives beyond just the first derivative. So the second derivative of a function, it's the derivative, which remember other words for that are the slope, rate of change, or rate of the first derivative of the function. So it's a derivative of the derivative. So all the same rules for derivatives still apply. It's just you take the derivative again of the. Once you take the first derivative, you take the derivative again to get the second derivative. So then the notation for the second derivative, instead of just writing one little mark there, you write 2, and that's f double prime of x, if it's a function in function notation. But if it's in a rate of change notation, it can be used for things that are not functions. You write d squared y over dx squared. That would be how you write the second derivative. Similarly, for the third derivative, you'd write f triple prime, you'd write 3 little marks there of x in function notation, or in rate of change notation, now would be a 3 there instead of a 2. If you go beyond the third derivative, the nth derivative, then instead of writing the little marks there, you put that number in parentheses. So with the seventh derivative, you'd write it like this with a 7 in parentheses up there. And then the 7 would be written there, because the seventh derivative would be like this. So let's look at some example problems. It says find the second derivative of the function. We're starting with y, so we first have to find the first derivative. But the first thing I want to do is notice it's 3 over x. If you leave it like this, it looks like we have to use the quotient rule. But since that 3 to the constant is actually helpful if you just move the x up there and think of that as 3x to the negative 1. That way you can see you just need to use the power rule and not the quotient rule. So the derivative of y, since it's not in function notation, would be written as dy dx. Derivative of 5x cubed using the power would be 15x squared. Plus the derivative of sine x is cosine of x. The derivative of negative x is negative 1. And the derivative of 3x to negative 1 using the power rule, negative 1 times 3 is negative 3. Reduce the exponent by 1, so it becomes x to the negative 2. Normally I would simplify this now if this was our objective with the first derivative, but since we're trying to find the second derivative, it's actually easier to leave it like this and just use the power rule again. So the second derivative in this notation will be written like this, d squared y dx squared. The derivative of 15x squared is 30x. The derivative of cosine x is negative sine x. The derivative of negative 1, the constant by itself, is 0. And the derivative of negative 3x to the negative 2 using the power rule, negative 2 times negative 3 is positive 6, and then reduce the exponent by 1, so x to the negative 3. And now, since this is our objective, let's go ahead and simplify the last term. So the second derivative would be 30x minus sine x plus 6 over x cubed. Now let's take a look at the next one. Here we've got f of x equals 3, and then cosine, you can see we've got 2x inside of cosine. So that's going to require the chain rule. So start on the outside. The derivative of cosine, well 3 just stays there. The derivative of cosine is negative sine. So that becomes negative 3 sine. Function inside 2x stays the same. But using the chain rule, that means we need to multiply by the derivative of the function inside. The derivative of 2x is 2, so times 2. And this time, before we take the second derivative, let's go ahead and simplify this just a little bit. Make our second derivative a little easier. We can bring that 2 out in front, along with the negative 3 to make it negative 6 sine of 2x. And again, we've got a function inside here, so when we take the second derivative, we're going to need to use the chain rule again. So f double prime of x, start on the outside, the derivative of sine is cosine, so that negative 6 constant stays out in front. Negative 6 cosine, function inside, 2x stays the same. But because we have to use the chain rule again, we have to multiply by the derivative of the function inside. The derivative of 2x is 2. And then if we simplify that, we get the second derivative, f double prime of x in function notation. 2 times negative 6 would be negative 12 times the cosine of 2x. Now let's take a look at where it says find the higher order derivative. And we're given the fourth derivative. That's what this means. is g of x sine of x, and we're asked to find the sixth derivative. So we have the fourth derivative, so if we had the original function, we'd have to take the derivative 6 times to get to this. But since we already have the fourth derivative, we only have to take the derivative twice. First time will give us the fifth derivative, take the derivative again will give us the sixth derivative. So let's find the fifth derivative. So here notice we've got g of x times sine x, so that's going to require the product rule. We'll take the derivative of that. So the product rule says we take the derivative of the first function, derivative of g of x we can write as g prime of x, times the second one as it is, sine x, and then plus the first one as it is, g of x, times the derivative of the second one, derivative of sine x is cosine x. And that's pretty much as simple as it's going to get. So now we can move on to the sixth derivative, take the derivative of the fifth derivative. But here, notice we've got a plus here, so we need to derive these separately. On each of them, though, it's going to require the product rule. So here we've got g prime times sine of x, and here we've got g of x times cosine x. So the product rule on each of them. So let's start with the g prime sine of x. So the derivative of g prime of x, the derivative of the first derivative would be the second derivative, g double prime of x, times the second one as it is, sine x as it is, and plus the first one as it is, g prime of x, times the derivative of the second one, derivative of sine x is cosine x. So that takes care of the derivative of g prime of x times sine of x, using the product rule. And then we've got plus, now we've got to use the product rule on g of x cosine of x. So we take the derivative of the first one, derivative of g of x is g prime of x, times the second one as it is, cosine of x, plus the first one as it is, g of x, times the derivative of the second one, derivative of cosine of x is negative sine x. And let's just simplify this a little bit. So the sixth derivative, you can bring this negative out in front on that term. And notice we've actually got a couple of like terms here. We've got a positive g prime of cosine x plus another g prime of cosine x. So this gives us 2 g prime of cosine x. So we leave the first term alone. We've got g double prime of x times sine x. And then we've got plus 2 this g prime of x cosine of x. And then we can bring this negative out in front to make it minus g of x times the sine of x. So that would be the sixth derivative. Okay, now let's start taking a look at some applications in the real world of these derivatives. And what we're going to look at today is position, which tells you where something is, velocity, which tells you how fast something is going and which direction, and acceleration, which tells you how the velocity is changing. So, the connection between these, velocity is the rate of change of the position function. And remember, rate of change is just another word for the derivative. So it's the derivative, velocity is going to be the derivative of the position function with respect to time. Time is going to be our variable here. And then acceleration is the rate of change, and that means the derivative of the velocity, because that's telling you how the velocity is changing over time. So here's how these are connected, and these are all referred to as instantaneous functions. That's what the derivatives really are, because they're telling you what's happening at one instant, in this case, one instant of time. The position function tells you at one instant of time where an object is at. Velocity tells you at one instant of time how fast that object is moving and which direction. And the acceleration tells you, again, how the velocity is changing at that instant. So, we started with the position function, which sometimes will be called s of t, but we'll use other letters for that. It's not always s of t. And if we want to go to velocity, velocity is the first derivative of the position function. And then if we want to go to acceleration, acceleration is the first derivative of velocity, but since the velocity is already the first derivative of the position, acceleration is going to end up being the second derivative of the position function. And then there's a slight difference between velocity and speed. Velocity can be positive or negative because it tells you not just how fast something is going, but in which direction. However, speed is defined as the absolute value of velocity. So speed can never be negative. It doesn't indicate direction at all. It's just how fast something's going. So just think about in your car, what measures how fast you're going. It's called the speedometer, right? It just tells you how fast you're going. It doesn't tell you which direction you're going. And notice there's no negative numbers on your speedometer. Right? 0 is as low as it gets because speed can never be negative. Now let's take a look at one position function we will be using is s of t equals negative 16 t squared plus v naught times t plus s naught times gives you the position function. This is for an object moving vertically near the Earth's surface. So you don't have to memorize this one, you just need to know how to use it properly. Again, anything moving vertically near the Earth's surface, we can model it, where s of t is measured in feet and time is in terms of seconds. And so what that little subscript of 0 means is v naught, as I say it, that's the initial amount of something. In this case, the initial velocity. In other words, at time 0, what's the velocity at the very beginning of the problem? And s naught is the initial height times 0. And in other words, it's the initial position, how high it is off the ground to start with. And then for the initial velocity, there's going to be some keywords in a lot of these problems you want to be careful to look at, because they tell you something important about the initial velocity. If something is thrown or launched upward, that means you're giving it some force upward and giving it some positive initial velocity. However, if something's thrown or launched down, then you're giving it some force downward, so it's going to have a negative initial velocity. And in the last case, if you don't throw it upward or throw it downward, if you just let it go or drop it, you're not giving it any initial velocity. You're just letting gravity do its work. So the initial velocity there is going to be 0. So again, look out for those keywords in the problems that tell you something important about the initial velocity. So let's look at this one. This one's, so the baseball is thrown vertically upward. So that tells us two things. So if it's vertically upward, we can use the one for the object moving vertically near the Earth's surface. And since it's thrown upward, that means the initial velocity is going to be positive. And it tells us that initial velocity is 46 feet per second. So our v naught is a positive 46. And it says by a player who's 6 feet tall, and you're assuming the player releases the ball at his height. So this is where the baseball starts, 6 feet above the ground, so that's our initial position. Now we can write our position function. It says find the position, velocity, and acceleration functions for the baseball. So the position function, which we'll call s of t, would be negative 16t squared, and we'll just substitute in our initial velocity and initial position we just figured out. So s of t is negative 16t squared plus the initial velocity 46 times t plus the initial position of 6. And then we take the derivative of that. It's not v prime, v of t, or velocity, which is also s prime of t, the derivative of the position function, be negative 32t plus 46. The derivative of 6 constant by itself is 0. And then the acceleration function, which is the first derivative of the velocity function, or the second derivative of the position function, derivative of negative 32t is just negative 32, and the derivative of 46 constant by itself is 0. Now let's use these to determine the height, velocity, speed, and acceleration of the baseball at a specific time at 2 seconds. Remember, these are all considered instantaneous functions. They tell you what's happening at 1 instant of time. In this case, 2 seconds is that instant of time we're looking at. So let's start with s of 2. That'll be negative 16 times 2 squared plus 46 times 2 plus 6. Well, 2 squared is 4 times negative 16 is negative 64. 46 times 2 gives you 92 plus 6. So 92 plus 6 is 98, minus 64 gives you 34. And the units for position are feet. So it's, at 2 seconds, we know the baseball is 34 feet above the ground. then the velocity of time 2, v of 2, would be negative 32 times 2 plus 46. Negative 32 times 2 is negative 64 plus 46 is negative 18. And the units for velocity here are feet per second. Every time you take the derivative here, you basically are dividing by seconds, the units for time. Take the derivative once, it's feet per second. And then the acceleration is, right here, there's nothing to plug in for t, it's just negative 32. And the units, well, velocity is feet per second, so you take the derivative again, that's feet per second. So feet per second. Per second, well, so you could write it that way, but instead of dividing by seconds again, that's the same as multiplying by 1 over seconds. So that becomes feet per second squared. And then finally, speed, remember, is similar to velocity. Notice our velocity was negative 18 feet per second. The significance of the negative, that means the baseball at 2 seconds is already traveling back down towards the ground. But the speed, remember, is the absolute value of velocity. So speed can never be negative. The speed of the baseball would just be 18 feet per second. All right, now let's look at something a little bit different. It's the average velocity. So this is different than instantaneous velocity. With average velocity, we don't use the velocity function at all, which gives us the instantaneous velocity. Instead, notice it gives us an interval. Whatever is an average is going to be over some interval. In this case, over the first 2 seconds, the interval would be from 0 to 2 seconds. So you're doing the average velocity. This you don't really use calculus at all. It's just the change in position over the change in time, because it's not at one instant. So we're not using the derivative. So change in position would be on 0 to 2. You want to know, well, what's the position at time 2, and subtract what was the position at time 0. And then divide that by the change in time would just be our interval there, 2 minus 0. Well, S of 2, if we hadn't already figured it out, we'd have to do that, but in part B, we already figured out S of 2 is 34. 34 minus S of 0, that's the initial position. You can either look right here, the initial position was 6, or if you plug in 0 in the position function, you can see that wipes out everything but the 6. So S of 0 is 6. Divided by 2 minus 0 is 2. So we get 28 divided by 2, which is 14. And you can see the units would be velocity, because all you have to do is look at the units right here in your fractional expression. The units for the numerator, position, is in terms of feet. The units for time is in terms of seconds. So we do get feet per second, which are the correct units for velocity. So that's on average from 0 to 2. We have a positive velocity, means on average from the first 2 seconds the baseball is traveling up more than it was traveling down. This is positive. And this next one says, what's the velocity of the baseball? It's really a 2-part question. The instant before it hits the ground. And the reason why it says the instant before it hits the ground, because once it hits the ground's going to stop the baseball, and the velocity is really not that interesting, it's just 0. But right before it hits the ground, in other words, upon impact, what's it impacting the ground with what velocity before the ground actually stops it? So whenever you see that phrase, when something's on the ground, in this case it hits the ground tells you something about the position. It tells you the position above the ground is 0. So we set S of t equal to 0. So let's go ahead and get our position function. The rule was negative 16t squared plus 46t plus 6, and set that equal to 0. And let's go ahead and factor that. Well, it has a GCF of 2, but since the leading coefficient is negative, it's easier to be factored out negative 2. That leaves with 8t squared minus, when you take out negative, it changes the sign of all the terms. 23 times 2 is 46, so 23t plus negative 2, oops, not plus, minus negative 2 times negative 3 gives you a positive 6. And let's keep factoring that. So it's a trinomial, so if we multiply the 8 times negative 3, factors of negative 24, whose sum is negative 23, What would work there? Well, negative 24 and 1 would work. So we have 8t squared. We split up the middle term using those two. Instead of negative 23t, we can write negative 24t plus 1t minus 3. Now we've got 4 terms, so we can group factor it by splitting it in half. The GCF of the first two is 8t. We take out 8t, that leaves us with t minus 3. The GCF of the last two is just a positive 1, but you still want to factor it out, so it's easier to see what's left. And what's left is t minus 3. So now you can see they both have a t minus 3 we can factor out. And the other factor left would be 8t plus 1. And then don't forget we still have the GCF of negative 2. So now that we've got completely factored equal to 0, now one of these has to be 0 in order to multiply these. Well, negative 2 could never be equal to 0. That's just negative 2. So either the t minus 3 has to equal 0, or the 8t plus 1 has to equal 0. Well, if you solve this one, you get t equals 3. 3 seconds. And then you solve this one, if you subtract the 1 divided by 8, you get t equals negative 1/8. So we got two answers, but let's think of it about if they make sense. Well, t equals 3, that'd be 3 seconds after the baseball is released. T equals negative 1/8, that would mean it hits the ground 1/8 of a second before the baseball is thrown. Now that doesn't really make sense because we don't have negative time, we're not going backwards in time. So negative times will not make sense in these real world problems. So we take t equals 3, and now we can answer. Now we know that when it hits the ground, now it says what's the velocity of the baseball when it hits the ground. So now we can plug that into a velocity function. V of 3 would be negative 32t plus 46. So negative 32 times 3 plus 46. That would be negative 96 plus 46 is negative 50. And the units would be, since it's velocity, feet per second. See, it's a negative because it does, in fact, it's traveling downward when it hits the ground. The reason why we're getting that negative time is one of our answers, even though it doesn't make sense. It's going to deal with a position function. The negative 16t squared plus 46t plus 6, that's a parabola that opens down because of the negative leading coefficient. So if we were to graph it, something like this, where this is negative 1/8, this is 3, we're getting those two when they set it equal to 0. However, this part doesn't really make sense because we're not going backwards in time. So that's part of the problem. Not relevant. And the parabola actually stops there because it doesn't start bearing on the ground either. That's 3, it just stops on the ground. So that's really the part of the problem that's relevant in this problem, just the part of the first quadrant, which is often the case with the real world problems. Alright, the next one says a particle travels along the y-axis. So it's moving on the y-axis according to the position function y of t. So notice they're calling the position function y of t, just to remind you it's traveling on the y-axis. So we're not using that position function we used before because that was only for things traveling vertically near the Earth's surface. And t is in seconds. So the first thing, part A, says at what time or times is the particle at rest? So this is another important two-word phrase here that tells you something important. At rest means it's not moving. If it's not moving, that tells you something about the velocity. That tells you the velocity, if it's not moving, has to be 0. So, we first need a velocity function. Well, v of t, remember it's the position, derivative of position, that's the same as y prime of t. So that'd be 6t squared minus 42t plus 60. So now we can take that and set it equal to 0. And factor it. As a GCF of 6 we can take out first. That leaves you with t squared minus 7t plus 10. And that factors further. Factors of 10, that have to be negative 7. Would be negative 2 and negative 5. Here we don't have to split up the middle term. Since the leading coefficient is just 1, we can use the shortcut factoring. And then if we set these equal to 0, 6 will never equal 0. If you set t minus 2 equal to 0, you get t equals 2. If you set t minus 5 equals 0, you get t equals 5. And the units for time are seconds, so both of these would be seconds. They're both positive, so they both do make sense. This is what timer times. In this case, there's 2 times. And then part B says, is the particle moving up, down, or neither time 1? Well, we're going on the y-axis, remember? So if we're traveling on the y-axis, this is our y-axis here. Well, if the particle is moving up, that tells us the velocity must be positive if it's moving up. Or another way of writing that, the velocity would be greater than 0. However, if it's moving down the y-axis, that tells us the velocity must be negative. Or another way of writing that, the velocity is less than 0. And neither, it's not going up or down, that must mean the velocity is 0. But we know it's not 0 time 1 because we just solved for that. When velocity is 0, it's at time 2 and 5. So it's got to be either up or down. So then we're going to give you a reason for our answer. So all we have to do is plug in time 1 into our velocity function and see if it makes it positive or negative. So v of t, or v of 1, we already have v of t right here, would be 6 times 1 squared minus 42 times 1 plus 60. Will be 6 minus 42 plus 60. That's 66 minus 42, gives you 24. Here the units would just be, smooth on the y-axis, so it's just units, and the units per time per second, so units per second. The significance, though, is that it's positive, 24. So that means it's moving up. So we can turn this question into a statement and say at t equals 1, the particle is moving up. And then the justification, the reason for your answer, would simply be since, when u is moving up, since the velocity is positive, so we don't want to say v of t, because that would mean the velocity is always positive. We want to say v of 1. The velocity specifically at time 1, that's what was greater than 0. Or you can say is positive. Now let's look at the same one, and now let's find again the average velocity over the interval 0 to 3. So remember, average velocity again is the change in position over the change in time. So remember, that's different than instantaneous velocity. Instantaneous velocity is what we just found right here. Time 1, instantaneous velocity was 24 units per second. Now we'll look at the average velocity. This interval 0 to 3, that would be our velocity position function is y this time, so it would be y of 3 minus y of 0, that would be the change in position, over 3 minus 0 would be the change in time. But this time we don't know what the position of 3 is. So we have to figure that out by plugging it into our position function here. 2t cubed minus 21t squared plus 60t plus 3. So y of 3 be 2 times 3 cubed minus 21 times 3 squared plus 60 times 3 plus 3. And I'll just simplify that. So 3 cubed is 27 times 2 is 54. 3 squared is 9 times 20 is 180, and then 21 would be 189. 60 times 3 is 180, and plus 3. So let's see, that'd be 183 minus 189 would be negative 6. 54 minus 6 is 48. So y of 3 is 48 minus y of 0. That's a little easier to figure out. Y of 0, if you plug in 0 in the position function, let's see, that's going to wipe out everything but the 3. So 3 over 3 gives you 45 over 3. That divides easily. It's 15. And look at the units. Units for position here are units. Units for time or seconds. So it's units per second. So that means on average, this is positive on interval 0 to 3. The particle is moving up the y-axis more than it was moving down the y-axis. Now let's look at the average acceleration, which is similar in how you calculate it to the average velocity. Again, this is different than instantaneous acceleration. We're not using the acceleration function at all. Average acceleration is the change in velocity over the change in time. So the change in velocity on interval 0 to 3 would be v of 3, velocity times 3 minus the velocity of time 0. That would be our change in velocity over the change in time would be 3 minus 0. So now we need to know what v of 3 is. So let's use our velocity function to calculate that. Remember our velocity function was 6t squared minus 42t plus 60. So 6 times 3 squared minus 42 times 3 plus 60. Go ahead and simplify that. 3 squared is 9 times 6, 54. 3 times 40 is 120. 3 times 2 is 6, so 126. And then 54 and 60 gives you 114. 114 minus 126 is negative 12. So we got v of 3 is negative 12 minus v of 0. Let's see if we plug in 0 in our velocity function. Wipe out everything but the 60. So that's 60 over 3 gives you negative 72 over 3. That divides evenly, that's negative 24. And the units here, units for velocity are units per second. And then units per time per second, so units per second would be units per second squared. Negative means on average, the velocity is decreasing over the interval 0 to 3. That's our average acceleration was. Okay. Now, another two-part one. This one says find the speed of the particle. It's our objective, but we're trying to find it when the acceleration equals 6. So first we need to know when the acceleration is 6, so we can set the acceleration function equal to 6. But so far we haven't needed that. We didn't need it for the average acceleration. Now we want the instantaneous acceleration. So a of t, remember it's the first derivative of velocity, v prime of t, which is the second derivative of position. That would be y double prime of t. So that would be 12t minus 42. So we'll set 12t minus 42 equal to 6. And solve for t. Add the 42 gives you 12t equals 48. And divide by 12 gives you t equals 4. So 4 seconds, that's when the acceleration equals 6. And now we want to know the speed at that time. So the closest function we have to speed is velocity. So if we plug that in our velocity function, v of 4, that would be 6 times 4 squared minus 42 times 4 plus 60. So 4 squared is 16 times 6 gives you 96. 42 times 4, that's 168. And plus 60. So v of 4, 160 plus 96 is 156 minus 168 gives you negative 12. That's the velocity is negative 12 feet per second. The speed, remember, can never be negative. It's the absolute value of velocity, so the speed at 4 seconds would be positive 12, so not the units per second. Now let's look at a position function where it says it's moving along the x-axis. And notice they call the position function x of t to remind you it's moving on the x-axis. So on the x-axis, draw it here. This is our x-axis. then just think which direction is positive and negative. If something's moving right on the x-axis, that means the velocity is positive. That's the positive x direction. If something's moving left on the x-axis, that means the velocity is negative or less than. So this one says determine the time or times when the instantaneous velocity equals the average velocity on the interval 0 to 2. So we've got both instantaneous and average in the same problem here. Instantaneous velocity, that's our velocity function, v of t. And that's just the derivative position function. So that's the same as x prime of t, which, use the power, would be 3 times 1/3 would just be 1, and then it reduced to x by 1, so t squared, minus the derivative of 2t squared would be 4t. So that's our instantaneous velocity. We want to know when does this equal the average velocity. Remember, it's the change in position over the change in time. In this case, our position function is x of t, so that'd be x of 3 minus x of 0 over 3 minus 0. So we need to calculate this average velocity, and then we can finish solving this for t. So x of 3 we haven't figured out yet. So that's going to be 1/3 times 3 cubed minus 2 times 3 squared. Well, 3 cubed is 27, divided by 3 is 9, minus 3 squared is 9 times negative 2 gives you 18. 18, 9 minus 18, it is negative 9. So that's our position at time 3. Minus x of 0, you can see if you plug in 0 in there, you're just going to get 0, it's going to wipe everything out. Over 3, so we get negative 9 divided by 3 is negative 3. So that's our average velocity on the interval 0 to 3, negative 3. So we want to know when does the instantaneous velocity, which is t squared minus 4t, equal the average velocity of negative 3. So to solve this, you would just add the 3 over, get t squared minus 4t plus 3 equals 0. And then factor that. Factors of 3, that would be negative 4, would be negative 1, and negative 3. Set those equal to 0. If you set t minus 1 equal to 0, you get t equals 1. If you set t minus 3 equal to 0, you get t equals 3. They're both positive, so they both make sense, and the units here are seconds. So there's 2 times this case. Now let's look at a similar question. This one says, determine the time or times when the instantaneous acceleration equals the average acceleration on the interval 0 to 3. So instantaneous acceleration, that's our acceleration function, a of t, which is also the first derivative of velocity, which is the second derivative of our position function. So if we look back here, our velocity function was, our first derivative position was at t squared minus 4t, the derivative of that would be 2t minus 4. So that's our instantaneous acceleration, 2t minus 4 equals average acceleration, or we don't use the acceleration function, this is not instantaneous, it's over an interval, that's the change of velocity over the change in time. So that's v of 3 minus v of 0 over 3 minus 0. And so we need to calculate v of 3, so plugging that in our velocity function here, which was t squared minus 4t. That'd be 3 squared minus 4 times 3, which is 9 minus 12 gives you negative 3. So v of 3 is negative 3 minus v of 0. If you plug in 0 in the velocity, you can see that wipes everything out. So it's just 0 over 3. So we get negative 3 divided by 3, that's negative 1. So that's the average acceleration on the interval 0 to 3, so negative 1. So we want to know when does our instantaneous acceleration 2t minus 4 equal the average acceleration of negative 1. So if we add the 4 over, we get 2t equals 3 divided by 2, 2t equals 3/2, so 1.5 units for time. In this case, there's just one time in the interval when instantaneous acceleration equals the average acceleration. Now, let's take a look at what is the velocity of the particle when the acceleration is 0. So this is another one of those 2-part questions. We want to know what's the velocity of the particle specifically when the acceleration is 0. So the first thing we need to know is when the acceleration is 0. So let's set the acceleration function equal to 0. That's 2t minus 4, we got it right here. So when is that equal 0? Well, I can add over the 4, you get 2t equals 4, divide by 2. So when the acceleration equals 0 is at time 2, 2 seconds. And then we want to know what's the velocity of the particle at that time. So v of 2, our velocity function was t squared minus 4t. So that would be 2 squared minus 4 times 2. So v of 2 would be 4 minus 8 gives you negative 4. Units for velocity would be units per second. So that means the particle would be traveling left on the x-axis at that specific time of 2. Finally, let's take a look at another one traveling on the x-axis, but this time we've got 2 particles rather than just 1. So it says the position of particle A is given by a of t, so that's one position function, negative 2 cosine of pi over 6t, and the position of particle B, another position function, is given by b of t equals 3t times the sine of pi t over 4. So part A says what's the distance between the particles at t equals 2. So distance, kind of like speed, is never negative. Either 0 can be the distance or it can be positive. Never negative. So if you want to know the distance between the particles at time 2, well, what's going to tell us the distance between them is their position. So we just need to find the position of each of them at time 2, see where they're at on the x-axis. So let's start with a of 2. Negative 2 times the cosine. When you substitute in 2 there, times pi over 6, that reduces to be pi over 3. And we draw where pi over 3 is. Make it 60 degrees in our first quadrant. The sides of the triangle there, square root of 3, 1, 2. And negative 2 times the cosine of pi over 3. Cosine, remember, is adjacent over hypotenuse, so that would be 1/2. So that would be negative. So now we know that's where particle A is. That is a negative 1 on the x-axis at time 2. And now let's find the position of particle B. So let's find B of 2. So that would be negative, so it would be 3 times 2 times the sine. You plug in 2 there for t, you get 2 pi over 4, which reduces to pi over 2. So 3 times 2 gives you 6 times the sine of pi over 2. Well, pi over 2 is right on our axis there. Our sine is the y coordinate, so it's 1. So that would be 6. If we draw this out, particle A we figured out at time 2 is over here, negative 1. Particle B at time 2 is over here at 6. So the way you get the distance between those two is just subtracting them. You can go 6 minus negative 1 gives you 7. So there's 7 units apart. That's the distance between the particles. Now in general though, we might not always have integers, and we might not even know necessarily sometimes if we're given some constants in there which one is larger. So if that's the case, remember distance can never be negative. Well, you can ensure when you're subtracting them, especially if you didn't know which one's bigger, you put absolute values around it, then you can make sure it's always positive and negative, never negative. That way, even if you started with negative 1 and then minus 6, absolute value, that would still be positive 7. So that way, it doesn't matter which one goes first. Finally, let's take a look at time 3. Are the particles moving in the same direction or opposite directions? Justify your answer. So remember, we're moving on the x-axis. So the thing that's going to tell us which direction they're moving in is the velocity. It tells us how fast something's going and in which direction. So now we need the velocity of each of them. Since we've got 2 different velocity functions, I'm going to use a little subscript of A. So the velocity of particle A at t, that's the same as A prime of t. We go back here, we can see we've got this function inside, pi over 6t, so we're going to need to use the chain rule. So when we take the derivative of that, the negative 2 constant in front stays out in front. However, when we take the derivative of cosine, the function on the outside, the cosine is negative sign. So that negative is going to cancel out the negative here, making it positive. And then sine of pi over 6t, function side stays the same. And then using the chain rule, it means we have to multiply by the derivative of the function side. The derivative of pi over 6t is just pi over 6. Just a constant, just like the derivative of 2t would be 2. So, times pi over 6. And now, let's go ahead and substitute in 3. So what we're really concerned with here is whether this is going to be positive or negative. So we've got 2 times the sine. When you substitute in 3, that becomes 3 pi over 6 reduces to pi over 2 times pi over 6. And we already figured out the sine of pi over 2 is 1. So this is 2 times 1 times pi over 6. That reduces to be pi over 3. But the importance in terms of what we're asked about here is not the value, the actual value, just whether it's positive or negative. In this case, that's greater than 0, that's positive. So we need to know A, particle A is moving right at time 3. Now we just have to figure out, is particle B also moving right or is it moving left? So we also need the velocity function for particle B. So V sub B of t, the subscript, since there's 2 different velocity functions, the same as B prime of t. So B, though, is a little bit more complicated derivative because we've got this t out front. It's not just a constant, it's 3t times the sine of pi t over 4. So here, we're actually going to need to use the product rule overall. And within that, since we've got this pi t over 4 inside there, we're also going to need to use the chain rule within it. But one thing about using the chain rule there, I wrote these specifically in 2 different ways. This is the easier way to write. Pi over 6t shows you can just take the derivative and treat this pi over 6 as a constant. If you leave it as pi t over 4, it might look like you have to use the quotient rule, which you could use, but it's easier if you think about it as pi over 4t to see you actually don't need the quotient rule at all on that part. So let's use the product rule overall. It says we take the derivative of the first one, the derivative of 3t is 3. Times the second one as it is, sine of pi over 4t. And then plus the first one as it is, which is 3t, times the derivative of the second one, the derivative of sine is cosine. Function side alone. And then the chain rule says we have to multiply by the derivative of the function side, derivative of pi over 4t. Pi over 4 is just a constant, is just pi over 4. Just like the derivative of 5t would be 5. And now let's go ahead and substitute in 3 to see if it's positive or negative. So 3 times the sine, we plug in 3 there, that becomes pi over 4, becomes 3 pi over 4. Plus 3 times 3, and that also becomes 3 pi over 4 inside of cosine. That's pi over 4. So let's go ahead and draw 3 pi over 4 here. 3 pi over 4 is in the second quadrant, our unit circle. This here is pi, which is the same as 4 pi over 4. This is pi over 4 less than it. So 3 pi over 4 is here. The size of the triangle is a 45, 45, 90 triangle. 1, 1, and root 2, except this one's in the negative direction. So v sub b of 3. 3 times the sine of 3 pi over 4. The sine of 3 pi over 4, sine is the opposite over the hypotenuse, so 1 over root 2, which is the same as root 2 over 2 when you simplify it. Plus 3 times 3 is 9. Cosine of 3 over 4, 3 pi over 4. Cosine is the adjacent over the hypotenuse, so negative 1 over root 2. and then times pi over 4. And let's just simplify this a little bit. Remember, we're just concerned whether this is positive or negative. So v sub b of 3. I was just going to leave this one 3 times root 2 over 2. I'll pull this pi over 4 out in front with a 9, so, and it's negative as well, so it's negative 9 pi over 4. Oops, I could have written 1 over root 2. It's root 2 over 2 also. Just pull the negative out in front. So they both have root 2 over 2. This is 3. This is negative 9 pi over 4. To see if this is positive or negative, you just have to look at the coefficient, see which one's bigger. 3 compared to 9 pi over 4. Well, 9 pi over 4 would be, if we round up pi to be 3, it would be 27 over 4. Well, 4 goes into 27, 6 point something times. So that's way bigger than 3, so you can see it, the negative term would be larger in magnitude, so this overall would be less than 0 or negative. Because it's less than 0, negative, that means B is moving left. So now we can answer our question. Opposite particles moving in the same direction or opposite directions, we can say T equals 3. The particles are moving in opposite directions. And then you can say since, for your justification, simplest way to do this would be say since v sub a of at time 3, the velocity of particle at 3 is greater than 0, and v sub v of 3 is less than 0. And that concludes the notes for AP Calculus on the topics of higher order derivatives and position, velocity, and acceleration.